This is the video on collisions and bounce. All right, so to understand collisions and bounce, we need to understand the law of conservation of momentum. Basically, what the law of conservation momentum states, momentum cannot be created or destroyed. It can only be transferred from one place to another. So momentum is like cash in a room. It can change hands, but the total amount will remain the same. So how can collisions be represented mathematically? So let's take a look at elastic collisions. So there's no lasting deformation, no heat generated, no sound generated bounce. Like I said, this is there's no such thing as a perfectly elastic collision. But for this case, we're just looking at it mathematically. Now, the equation for the elastic collisions is this equation off to the right. The left side of the equation is before the collision, and the right side of the equation is after the collision. They are set equal to each other because of the law of conservation of momentum. Now, notice how the mass of the objects do not change, but the velocities do. So the velocities after the collision, right, are v1 prime and v2 prime. So essentially the variable v means that's the velocity. The subscript represents which object, and that prime means the velocity will be different after the collision. So it's just a way to denote those different variables. So let's take a look at a problem that we can have. So the red card has a mass of 3 kilograms and an initial velocity of 4 meters per second. The blue card has a mass of 1 kilogram and an initial velocity of rest. The cards collide in an elastic collision. After the collision, the red card has a velocity of 2 meters per second. What is the total combined momentum of both cards before the collision? What is the total combined momentum of both cards after the collision? What is the velocity of the blue card after the collision? All right, a lot to take in here, but essentially we're looking for that velocity of that blue cart after the collision. So I know everything there, right? So I know the red cart's mass velocity, I know the blue cart's mass velocity before the collision, and I know the velocity of the red cart after the collision. Now, I'm looking for, all I do is I plug everything into that equation for the elastic collision. Now, what is the total combined momentum of both carts? Well, 3 times 4 is 12, and 2 times 0 is 0. So I have to have 12 kilogram meters per second before the collision and 12 kilogram meters per second after the collision. Knowing that, I can just solve for the velocity of that blue cart after the collision. So now let's take a look at inelastic collisions. So inelastic collision, remember permanent deformation, basically the objects stick together. Now momentum cannot be created or destroyed. This is the equation for an inelastic collision. So the left side of the equation is before the collision. The right side of the equation is after the collision. They're set equal to each other because of law of conservation of momentum, and the objects stick together and combine to become one object after the collision. That's why the masses are added together, and this is also why there's only one velocity after the collision. I only have one variable. So let's take a look at an inelastic collision problem. So the red card has a mass of 3 kilograms, initial velocity of 4 meters per second. Blue card has a mass of 1 kilogram and initial velocity of rest. The cards collide in an inelastic collision. What is the total combined momentum of both carts before the collision? What is the total combined momentum of both carts after the collision? What is the velocity of both carts after the collision? So notice this is the exact same problem we did with the elastic collision, but now we're doing an inelastic, so they stick together. So I'm looking for that velocity of this combined cart after the collision. So I plug everything into the equation. I know the total combined momentum of both carts before the collision is 12 kilogram meters per second. So that means I have to have 12 kilogram meters per second of momentum after the collision. So I plug everything in and I solve, and that cart's going to be going 3 meters per second after the collision. So let's take a look at this question, right? And this does have to do with bounce. It does have to do with law of conservation of momentum. Why aren't cars made to bounce for safety? Why don't we have rubber cars? So if we take a look at a car or a truck hitting a tree, we know that each of those objects force the same force, the same magnitude of force. You know that they're applied at the same time for the same amount of time. We know that they don't cancel because they act on two different objects. We know that they experience the same impulse because if the force is the same, the time is the same. Now, which object experiences greater momentum? Both the same because of the impulse is change of momentum. Now, the effects are different because essentially that tree is going to have a much larger mass. So the change of velocity is going to be a lot different. Notice how that tree doesn't really move. I mean, it is connected to the Earth, so it barely notices it because it has such a large mass. But that truck or that car goes basically from driving to stopped, right? Very large change in velocity. So let's take a look at this. Let's look at a car driving and in an inelastic collision, right? So I have a 1,000 kilogram car. It's moving toward a rigid wall or a tree, 20 meters per second, and from the time it impacts the tree to the time it stops, it's going to be half a second. So use this equation, right? So I'm going to plug it in. I'm going to find that force that it's going to take to bring this car to rest, negative 40,000 newtons. Now it's negative because we'll notice it's moving in the positive direction. Well, I'm going to need to apply a force in the negative direction to bring it to a stop. So now let's look at another problem. Now I have a car that bounces. So it's driving towards this rigid wall or tree, but this time it bounces in the opposite direction, going negative 20 meters per second. It takes the same amount of time. I plug everything into this equation, and now I get my force is negative 80,000 newtons. Now, here's the question, right? Why would you want to be hitting the head with a flat or a full ball? Like, what would you want to be hitting, right? So we know that the impulse and the change of momentum are going to be the same for both objects. Now let's take a look at a flat ball versus a fully inflated ball. Now, which of these scenarios does the ball experience a greater change in velocity? It's going to be the bounce, right? Because not only does that ball have to come to rest, it has to go in the opposite direction, so in the negative direction. So basically, it's two impulses: one to slow it down, one to launch in the other, one to speed it back up in the opposite direction. So the person experiences a greater impulse because those impulse pairs are opposite and equal. So if the ball experiences a greater change of momentum because it has to stop and then go the opposite direction, well, that the person's head is going to experience that impulse as well. So it's going to be larger than if it was a flat ball that just stopped. So to see this, whoops, oh, there we go, right? So to see this, we did the bounce lab, right? So in this lab, you have the same length string. You've got a bouncy ball on one string and a koosh ball on the other. The koosh ball will just stop, and that bouncy ball will bounce off of it. So they have the same mass. We lift it up to the same height, so they're going the same velocity when they hit the block of wood. Now the block of wood is going to fall over when the bouncy ball hits, right? So let's see here, right? So larger change of velocity. That bouncy ball is going to experience a larger change of velocity because not only did that bouncy ball have to stop, it's going to go in the opposite direction, in the negative direction. Well, the koosh ball just had to stop, go to rest. Now, experience a larger impulse. Well, remember, impulse is force times the time interval, or mass times that change in velocity. And we know that if they have the same mass, the change in velocity is going to be a lot larger for that bouncy ball because not only did it have to stop, it had to rebound in the opposite direction. So that's why the block of wood would fall over if that bouncy ball hits it, because basically that bouncy ball applied two impulses to that block of wood, right? One when that bouncy ball slowed down to rest, and once when it launched in the opposite direction. So once again, there's just too much unknown in the universe to take a break from learning. Get out there and question everything. All right.